Hi, I'm Songhyun Park from Qualcomm AI Research. Today, I will present our work, memory-efficient fine-tuning diffusion transformers via dynamic patch sampling and block skipping. Our target task is personalizing text-to-image models with only a few images. With DIT-based T2I model becoming deeper and larger, fine-tuning quickly hits a memory and compute bottleneck. Also, many existing efficient fine-tuning techniques were mostly validated on UNet backbones, so DIT fine-tuning remains relatively underexplored. To understand those bottleneck, training memory has three major components. First, parameter memory, the model weights resident on the GPU. Second, activation memory, forward and backward intermediates saved for backpropagation. Third, optimizer state memory, for example, Adams momentums for trainable parameters. A key challenge is that many approaches reduce only one of these components, so the total memory footprint can remain high. One common approach is quantization to reduce parameter memory. It can shrink the weight memory, but it may introduce performance degradation. Another approach is gradient checkpointing, which reduces activation memory by discarding activations and recomputing them during backpropagation. The drawback is that it increases computational cost due to the recomputation, which is undesirable for practical on-device personalization. Finally, PFT methods like LoRa reduce optimizer state memory by training only a small set of parameters. However, fine-tuning still requires backpropagation through the network, so parameter and activation memory can still dominate, especially for large DIT backbones. So we need a solution that reduces training memory more holistically. Our key idea is to reduce training memory via two orthogonal forms of sparsity, spatial and architecture. First, activation memory proportional to the number of patches, so we reduce it by sampling patches conditioned on the diffusion time step. This is dynamic patch sampling. Second, parameter memory is proportional to the number of fine-tuned blocks, so we skip non-essential blocks and reuse pre-computed residuals. This is block skipping with residual features. Let me start with dynamic patch sampling. In diffusion, timestamps align with what the model learns. At large T with high noise, the model focuses on global structure, and at small t with low noise, it focuses on fine details. So we choose a patch size based on timestamp, crop the image, then resize to a fixed low resolution. This preserves the running behavior across time steps while significantly reducing activation memory and compute cost, because we train on smaller effective inputs. Next is block selection. In units, layers naturally correspond to resolution stages, but DITs keep constant spatial resolution, so layer loss are less obvious. We ask which blocks are essential for personalization. We mask cross-attention in certain block ranges and measure the semantic drop. The key finding is that mid-level blocks are crucial. Masking them collapses subject identity. So we should preserve those blocks for fine-tuning and avoiding skipping them. With that insight, we skip the first n and last m blocks and fine-tune only the mid blocks with LoRa for personalization. However, naive skipping breaks the forward pass and causes degradation. To fix this, we pre-compute residual features for skipped segments delta f, and during fine-tuning, we add the residual features back to the forward pass so the model effectively approximates the skipped computation. This allows us to offload skipped blocks to reduce parameter memory and reduce optimized state memory since only selected LoRa modules are trained. Now to the result. The left table shows that DIT block skip maintains LoRa comparable subject and text fidelity across skip ratios. In the upper right graph, you can see the training memory drops sharply with our method. Then in the bottom right graph, We also observe lower trip levels during per iteration, and this remains favorable even when accounting for the pre-compute overhead for residual features. Overall, the takeaway is simple. We get large memory and compute savings without sacrificing personalization quality, enabling much more practical DIT fine-tuning under tight resource budgets. Finally, here are qualitative results. The main takeaway is that our method is qualitatively comparable to LoRa for personalization while using a much more memory-efficient fine-tuning. In particular, compared to several baselines, our method preserves the subjectivity and while maintaining good text prompt alignment. Thank you for your attention.